Thank you, Jean, for this nice introduction. And so basically, why do you want to do video understanding? It's quite obvious. There are huge amounts of videos available today on the internet, on YouTube, in film archives, and it's a daunting task to search for these videos. What we want to do is to either classify short clips or classify events. So this is, for example, examples from the TrackView Multimedia Event Detection Challenge. And then what we also want to do is we want to go into more detailed understanding of the video content. So one example is self-driving cars. There you have a continuous stream of information coming in, and what you want to do is you want to detect pedestrians which are going to cross the road, or for video surveillance you want to see who of the people are having some abnormal behavior. So these are things which current computer vision techniques are able to do, but what we would want to do in the long term is to really describe precisely the content, so not just detect certain actions, but really to see who is there, what are their interactions, what are their intentions. So here, for example, as the head waiter takes them to a table, they pass by the piano, the woman looks at Sam, and so forth. And this would be then the output, complete description, and then you would be able to search for the full video content. And so what are the difficulties in action recognition? So object recognition is already difficult, but in action recognition you can have viewpoint changes. The interclass variations are even more significant than for objects. And in addition to that, you can have camera motion. So here, for example, you see an example that there is a change in viewpoint. So here, for example, the person is eating. Second example is eating also, but the person is lying down, so it's a completely different viewpoint. Then here, you can see that there's large interclass variations. In both cases, the people here are eating. At the top, it's actually a monkey eating, and on the bottom, it's people eating at the dining table, and you can see that it's completely different. So you have to capture these large interclass variations, and then you also have camera motion. So you can see here, for example, the camera is moving, and then here again you can have shakes. The camera is shaking, so you have to actually stabilize also the camera in order to be able to recognize the actions. And then another problem, so these are the appearance changes in appearance, and what's even more difficult is how to collect the training data. So there are many action classes. Action classes have actually vocabulary which is not well defined, and many of them occur rarely, so really have to work around these problems to see how you define these action classes. And one of the approaches we'll show in the end is that you actually learn this from the data itself and not by annotation. And then some of the approaches, they look actually at action recognition from still images. They interpret the human pose and the objects the people are interacting with. More recently, people have implemented this multi-stream architectures where they detect objects, humans, and interactions. But obviously, if you're looking at video, what you really want to do is you want to measure the motion information, which is then helpful to disambiguate or even recognize from scratch the action. So for example, here, from the image alone, you cannot tell if the person is opening or closing the door. So you really need the motion and the stream of images to get the idea what the action is. And then on the other hand, you can see there was psychological experiments, where you can actually show that just by having the light bulbs on the people, you can very well see what kind of action the person is performing. And even you can tell if it's a child or a male or female who's walking just based on the motion. This is just to answer the question, why do we actually need motion information? And then basically, I'll give an introduction to optical flow, which is one way of capturing the motion information. So if you have the optical flow, what you know is how the objects or the pixels in the frames move along the video. So this gives you one information on what the motion is. And then I'll give techniques, an overview of techniques for video classification, and then action localization. So what is optical flow? So optical flow, what you have a 3D object moving in an image, and if you project it down, then the flow gives you actually the motion of the 3D image, 3D object in the image. And basically, you also have the apparent motion. So basically here, ideally the optical flow would be the same, but basically if you have a sphere which is moving around, you also get this apparent motion, right? So basically these are two things which causes the optical flow. And then what's the definition? Given two frames, in the first frame you take a pixel and you look how it moves into the second frame. So this gives you the flow field. This is the definition of the optical flow, where you actually estimate the apparent motion between the first image and the second image. And then what can you use this for? You can use it to measure how people move around the scene. You can measure what is the camera motion, and you can determine how to factor out things. And then there's a lot of literature on optical flow estimation. And the traditional methods, what they have used is the brightness constancy assumption. So what it assumes is that a pixel which is projected from 3D into the two images has the same appearance. It doesn't change appearance. And then it also assumes that points do not move very far. I'll say in a minute why. And then spatial coherence, points move like their neighborhood. So you see these are actually quite strong assumptions. And so basically, why do you assume this brightness constancy assumption? Then you can use the derivatives to derive optical flow constraints. You can then add spatial coherence and smoothness constraints and add matching terms. So all this has been optimized for a long time. And then recently, people have actually used deep CNN-based approaches. And so the question was, John is actually asking what is optical flow for? And so basically, here I think what's nice is to motivate how things move in the video and how it's estimated. But then if you look at the networks, basically what you can actually show is that you can either replace them and learn the whole thing end to end, or what we have shown recently, that if you have these 3D convolutional filters, you can actually approximate, you can distill the optical flow information into the 3D convolutional architecture and learn the two things at the same time. But what you cannot do, or what is not there today, you cannot completely automatically, without initialization, learn the optical flow. So by adding the optical flow, you still gain something. And I guess this is like the recurrent discussion. What kind of supervision do you need, and what can the system learn by itself? So basically, if the system learns everything by itself, it would obviously, if you just give a video input, it would obviously learn the optical flow. But then, basically, given that things are not perfect, or that our training architectures today are not perfect, you need this as some kind of initialization. And I'll get back to this in the last part of my talk when we do self-supervised learning. So again, you should think that if you initialize from random and from optical flow, it would give the same results. But then given on the convergence probabilities, you don't get exactly the same results. So it can be useful, for example, as a training signal or as initialization, and in the long term, maybe I'll just go away. And then basically, so here, the convolutional networks, what you have is you have an input 2 frames, 2 adjacent frames t and t plus 1. You have a convolutional network, and what you get is as output the optical flow. And so here, what you use as encoding for the optical flow is the color gives you the orientation, and the brightness gives you the strength of the optical flow. And so then 2 questions. What kind of network do you use? So here, what this approach uses, and it's kind of similar to what many people use for this kind of task segmentation optical flow treatment on the image level pixel information, is they use these unit type architectures where you first have a set of convolutions which go down in resolution and capture more and more of the context information. In the end, they have like a 1,000 dimensional signal which captures the representation in the image. And then what they do then, they have the refinement steps where they have the up convolutions, where the down convolutions go in as a signal. And basically what they do is they take the context information, take these different levels of information, upsample it, and then get the optical flow information out. And so this is the first thing. And then the second thing is what kind of data do we use? So basically annotating optical flow is impossible. And basically, so what they have used is the synthetic information. So it's actually quite nice. It looks completely arbitrary, but it does allow you to actually learn very good models of optical flow. And again, obviously, if you fine-tune on real data, you get an improvement of the performance. But I think this is like a nice story which shows that synthetic data in many cases can help you actually to learn a relatively good model, in particular if you cannot annotate large quantities of information. And then here, a refined version, what they do here is the first version just takes into account small displacements, and then if you have larger displacements, what you have here in addition is a warping layer. So in addition, you do the warping, and the warping helps you to auto-correct the thing, and that's actually a technique which is also used in the multi-scale version of traditional optical flow methods, where you also do the warping and then re-estimation to refine the optical flow. And then the second contribution of the second paper was that they they implemented the synthetic data in 3D. So here they show if they have a 3D version of the synthetic data, you can further improve the results. And actually, here you also have the, I know John is frowning again, but what you have here as well is like the objects which are segmented out, and actually we can use that also to learn actually foreground and background segmentation from the synthetic data. And so again, this actually shows that the synthetic data can be very useful because you can produce large quantities of this data for free, basically. So we didn't. So this is not our data set, right? This was done by Thomas Brock's. They don't have motion blur, and I guess that's something you could add, right? It's not something. And I guess that's like one of the questions: what kind of transformations do you want? And if you add motion blur, I mean that's what you did for your image super resolution. If you add motion blur, then you can show that you can use that to improve further results, right? So, and then. I mean, then if you look at the table, so there are like a lot of benchmarks, there's Sintel, Kitty, and then all the benchmarks, Middlebury, and they actually, these benchmarks vary on the displacement, the size of the displacement between neighboring frames. So if you have very strong displacements, the performance goes down. And so basically what you can see here, that this FlowNet 2 outperforms the traditional methods, and what is measured here is the endpoint error, so the endpoint error between the optical flow, estimated optical flow and the ground truth. Skip over this quickly. So just if you look at the results, you can see here, basically, this would be the 2 consecutive frames. Here you would have the ground truth, and then you can see the different results of the encodings, and you can actually see that the results produced here are largely better. They're not perfect, but they're largely better. And then, so basically what the conclusion here is, that basically approaches such as evenless optical flow, for which people have developed a lot of complex machinery, can now be estimated for using synthetic data and CNN with state-of-the-art performance. And what people are looking at currently is how to have smaller networks with the same performance by using, for example, distillation, or just learning them from 3D convolutions or static images. So that's what John said before. Okay, and then the next part, what you want to do in many cases is to classify the actions or the activities in the videos. So you have a clip or a longer video, but in general it's like an intermediate sized clip, and you want to see what are the labels which you can attribute to the video. So basically here you have a short video where the person is making a sandwich. So you want to classify that in this clip, making a sandwich is present and feeding an animal is not present. So you want to have labels assigned to the clips. And then the second task, which I'll attack in the second part of the talk, is to go into much more detail and to localize actually where in the videos which action is present, to really see what the people are really doing. And so what's the advantage here is that you really know at which point in time a person is performing which action. And so basically the two of them have different applications. So the first one would be just if you want to search for clips on the video, then you would use the first technique, and the second one would be, for example, if you want to localize somebody's falling down, somebody's putting down a bomb or something like this. And then for the action classification in videos, so the initial approach was developed based on space time interest points. I'll go into details in a minute, and then basically people worked on dense trajectories. And more recently, people have proposed this video level 3D convolutions. And so what do these space-time interest points do? What they capture the locations in the video where things move in space and time. And so what they do, they extend the Harris corner detector, which measures the autocorrelation of the signal and image to 3D. So what you do is you look how the signal correlates in 3D in the video, and you look at locations where there's like high, strong correlations in space and time. And then once you have the space-time interest points, you describe them by histograms of spatially oriented gradients and optical flow. And so here again, using this type of architecture, you can show that two types of approaches, optical flow and appearance, helps. And I guess this is because basically you were not extracting the same type of information. In one case, you based on just one frame. In optical flow, you look at the neighborhood structure, right? So basically you could say is by adding this neighborhood structure to the RGB, you can improve the performance as well. And once you have that, at the time people used histograms of visual words and SVM classifiers to describe the actions, and use this as an initial approach for action classification. And then next step was to go away from just these points, but move more towards trajectories. And so this is maybe something which people are now also today looking at, how to measure this temporal correlation in videos over a longer period of time. I'll get back to this at the end of my talk. And basically here, the dense trajectories, what they did, they sampled points at every scale, at multiple scales densely, and then used the optical flow to track the points in the space-time volume, had a description based on, again, these histograms of gradients, flow, and other types of descriptors. And if you look here, what you get a complete representation of the image where the points are followed along by optical flow. Then, as I said before, you can describe these points. Again, you can quantize the descriptors based on histograms of origin gradients. So these are basically the two state-of-the-art techniques up to 5 years ago. And so then what people have looked at recently is they have looked at how to use dense architectures for videos. So the first approach was by just having each frame represented by an appearance coordinate and a temporal coordinate based on the optical flow. This is just like a straightforward extension of image classification techniques to video. And so here, again, what they showed is that by adding the optical flow, the performance improved by a few %. And then this was like the initial approaches. And then obviously what you really want to do in video is you want to not take video as just individual frames. You want to look at the spatial temporal volume and characterize the spatial temporal volume. And so then what people have designed next is 3D convolutions. And so what you do, instead of just doing the convolutions in the image space, you have 3D filters which you convolute in space and time. And then one thing which has shown also to further improve the performance is to have the network trained or pre-trained on a large data set. And so there again, I think it's something which we have to do today because we don't know, we have to do today because we don't know how to learn these networks from scratch with little data, but basically in the long term, again, it's something we could get away with. And just to give an explanation how these filters work, so on the left, you see just spatial 2D convolutions. Then you could just have these 2D filters evolve as a block in the spatial temporal volume. But then what the 3D convolutions do, they have the small cuboids which evolve in space and time. And so they capture really how the information evolves in the video volume. And basically, what you could hope for is that these convolutions also learn the optical flow, right? So this is something which people look at today. Can they reproduce the optical flow? And for now, it's not learning it completely from scratch. And then if you look at what these filters learn, so basically here we compare different sizes of 3D convolutions. And so here what it shows, the region which is highlighted in green, shows actually where these convolutional filters fire highest. And you can see that it captures nicely the moment, similar to space-time interest point, the moments in time where there is a strong action which is performed. And so what you show here is basically if a filter highlights for a specific class. So we show the filters here in this set, which give the highest responses or the most consistent responses for a given class. So here again, you can see that the moments where really the action is performed, the performance is better. And then here, the second experiment is if you input into your 3D convolutions a smaller stack of frames, so only 16 frames, you can actually show that the performance is lower. So you can really see if you have this larger convolutional kernels, you get a better performance because you capture more of the dynamics of the video. And then, so basically, then people have developed different methods for these 3D convolutions. So basically, now the second approach was they inflated the inception network into 3D, and then other people have now inflated ResNets, who can really take any of the standard 2D architectures and port them to 3D. And then second point is that if you use this kinetics data set, you can have a further gain in performance improvement. Okay, and so basically, so video classification is something which people nowadays know quite well how to do. And the harder problem is actually the action localization. So to really say where in space and time a person is performing an action. And so again, initial approaches, they're just frame-based, so they looked at every frame, took bounding boxes in the frame, classified them as performing a specific action, yes or no, and then these actions were linked over the video, and then you could have a sliding window technique which localizes the actions in space and time. And then here, for example, an initial architecture where you have one stream of the faster RCNN network which is applied to RGB frames. So faster RCNN, what it does, it localizes region proposals. So it learns where the potential locations and boxes where the humans are present, because it's trained on human detection. And then basically it has another layer where it classifies these boxes into specific foreground or background, and foreground is classified in different action categories. And you have a box regressor, which actually adjusts the box to the human performing the action. And what else is happening here? You have, again, two streams, the RGB stream and the flow stream. The two streams are pooled at the layer of combining the boxes, so extract boxes from RGB and flow. So the flow boxes are actually extracting humans which are in movement. Combine these boxes together, and then you have two different types of features extracted for each of the box, one based on appearance and one based on flow. And then you combine this together, and you get the classifier for these boxes. And then obviously a thing of this is a suboptimal, because what you really want to do is to capture how these objects or these actors evolve in time. You have a little bit of information captured by the optical flow, but if you really look at what's going on, so here you look at this frame, you don't know if the person is sitting down or standing up, so you really want to have the temporal context to determine if the person is sitting down or standing up. So here you can see, if I have actually the adjacent frames given, we can see if the person is sitting down or standing up. And so then an initial approach which was developed, so there's a couple of approaches around which address this problem, was actually to not look at just one frame, but to look at what we call here anchor cuboids, which are fixed in space and time over the video. So you have these rigid volumes which you fix in space and time over a video volume, and then you train at the same time a classifier for this video volume, and then you also regress these tubelets to adapt per frame to the actor. So basically, initially the volume is rigid, and then basically you regress this volume to the correct tublet, and this allows you to adapt actually the boxes to the precise location of where the actor is. You can really refine the location of the actor on the fly. And so how is this done? So this is the approach is based on the SSD detector. So the SSD detector, how does it work? It doesn't extract bounding boxes. What it does, it has a set of multi-scale convolutions. So here, convolutions at different scales. And each of these outputs gives you the response for a given input size. So here, this would correspond to this region in the image. So for this region in the image, it says if the person is performing an action, yes or no. So you have these different resolutions, and at each resolution, you have for a given size the output. This is the SSD detector. You can obviously train this for human action detection. And so what we do here is we have these spatial temporal volumes extracted. We classify, we have a stack of SSD detectors for which we share the weights. And then we have a set of additional layers on top of this, where we actually stack the information from the different frames together. And then on this stack of descriptors, we have a classification stream and a regression stream. And so what the classifier does, it jointly sees the information over a set of frames. Let's say here it's 15, over 15 frames. And you can then determine if in this spatial temporal video volume you have the information present or not. And then the second thing is the regressor. So the regressor has actually, depending on the size of the input stack, number of four coordinates per frame. So if you have 10 frames, it will be 40. For each of them, it predicts actually where precisely the actor is localized. So it really does the regression to the precise localization of the actor, and it's actually nice. It works better if you do this regression over the spatial temporal volume than if you do it per frame. So you can really show that this helps you, the context information helps you to better regress the position of the actor. And then if you look at the quantitative results, so what you measure in general is action detection accuracy with AP, average precision criteria, given a certain overlap threshold. So 0.2 means that the intersection over union measure is 20%. It's relatively badly localized, but given that the localization is in 3D, so in space and time, this is still like reasonable. And then if you look at, like, if you want to have it quite precisely, the performance goes down. So one of the problems here is not only the classification, but also the localization, the spatial temporal localization of the action. Okay? And so you can see here that our approach outperforms the state of the art, and in particular for precise localization. So if you really want to localize precisely where the action is, our approach allows to refine the boxes. And so if you look at the performance, so you have in yellow the ground truth, in green the detections. And so you can see here we have detected correctly, have localized correctly the action, but the label is also correct. So here you would have like this high jump label detected correctly. And then here skiing, so you can see actually the localization is pretty accurate here. And the classification is also correct. And you can say, of course, classification is quite easy because the context information gives you already a lot of information here. You're riding bike, trampoline, jumping. And then here 2 failure cases. The first failure case is the localization in time is not very accurate. And the second case is that 2 people are moving together, and given that our approach is just based on these bounding boxes, it cannot model the context information correctly. And so this kind of shows a limitation of the approach, that if there's too many things going on, the model is not appropriate. So you have to have a more precise model, which really models how 2 people are moving together. And the first part was this temporal action localization in many cases is actually a problem because it's pretty ill-defined. You don't know exactly where the action is taking place. And so it's hard to measure it precisely. And then the second thing which we have seen here, so these results are all nice. And this is one of the state-of-the-art data sets, UCF 101, 24 action categories. But if you look here, it's quite simplistic. The actors, in many cases, in the middle. The actions are simple. In many cases, you could just do the prediction based on the surrounding scenes. And so if you look at what other data sets that there are around, so we've seen the sports data sets, then there are some other data sets which are very small. They only contain 21 action classes. They're very short. And then here are other data sets which are a bit longer, but again, the number of actions is very small. And so then one thing we've been doing is like to collect a better data set. And that's kind of what I said in the beginning. It's very difficult to define these actions. It's very hard to collect these data sets and to put them up for use. And even if you don't want to use them for training, you have to have some kind of measure of evaluating the performance. And here, you want to have data sets for which it's still hard and you want to measure progress, right? So if you have data sets for which everybody has like more or less 90% performance accuracy, they're too easy. And so what we have done here, we have defined a data set which is a large-scale collection and which contains atomic visual actions. And so what are atomic visual actions? It's actually actions which are like simple actions which you can then compose. So examples would be walk, talk to, stand, carry, hold. And basically, what we also have, A, it's exhaustive, so every human is annotated, and B, we can have multiple labels for each action. So basically, in general, people are not only performing one action, but in many cases, you're sitting, you're listening, you're watching, doing many things simultaneously. So it's actually important to have these multiple action labels which use together. And then here, just to illustrate the idea of why atomic actions, in many cases, activities are actually composed of these atomic actions. So here you can see, for example, the behavior, step down from the curb, cross the street, walk to school. So you have all these very small steps which people actually are performing. And then once you have that, you can compose like going to school or whatever, it can compose a high-level activity from these basic human actions. Anyway, that was kind of the motivation for defining these atomic actions, and also it's kind of one way of getting away from these high-level activities, which are in many cases very ill-defined. We have here 3 categories of atomic actions. The pose of the person, for example, stand, sit, walk, kneel, swim. You can have interactions with objects, so drive, pick up, carry. So this is very important because basically what you want is you want to not define every action with respect to the objects, but you would want to have the action, so carry, for example, or pick up, and then you can just have the object as an additional information and combine the different actions with different objects and have then multiple high-level activities. And then also another category which is important is human-human interaction, so handshake, talk to, hug, fight. And then as I said before, we have multiple labels per person, and we have an exhaustive annotation of all the humans. Here, a few examples of the activities, and then if you look at what we have these relatively short clips for which we have the location and the action annotated. So here, for answering phone. Another one would be clinking glasses. Another example here, hug person. And then for the annotation, as I said before, it's actually very hard to annotate precisely the start and end time of an action. So what we have done, we have subsampled 1 frame per second, and we've annotated this 1 frame, basically supposing that the neighboring information is likely to contain the same actions, but this goes away from very precisely annotating the start and end time, which is in many cases very hard. And then we've annotated 200 videos where we annotate 15-minute intervals. And so what's the idea of annotating this longer intervals is actually to have an exhaustive annotation of a whole chunk of videos to see how these things follow up, how they evolve over time, and also to not have these very short clips, but to have more long-term information.
You annotated that yourself?
Me? No.
No, your students.
Yeah, somebody annotated it. Yes. Yeah, no, John doesn't like annotations, but I think it's actually very useful because you have to have some kind of, at least some kind of evaluation protocol, right? Because basically what we're discussing the other day is even if you learn everything weekly supervised, which maybe in the long term we can hope for, you have to have still some way of evaluating what's going on, right? And if you have no annotations, you can always claim it's working. And it's kind of a very hard problem, right? Because basically for videos, it's much harder than images. For images, it's already quite hard to get the annotations, but for videos, it's intrinsically, I mean, as you say, it's very time-consuming and very ill-defined as well, right? Because what precisely do you want to annotate, which time frame? And so here what we did is 15 minutes because we wanted to have some kind of continuity and not just annotate like short actions in one short clip, right? Because then you can never ever learn anything about how these things evolve over time. And so the hope here is that we could, with this 15 minutes, you could see how things evolve over time, how they're correlated, and put it together as a nice story. And this is even this, like now we have this data, and even doing this now, it's really hard, and it shows how hard the problem is still, right? Because just getting the tracks correctly in these videos, it's very hard. To associate the people is hard, and then just like measuring how they interact and how they evolve over time is actually. So basically to have a full description, because the idea would be then to have a full description for this 15 minutes of video material, and it's actually still an open, challenging problem, right? So that makes the data set actually quite interesting because you can really do a lot of things with it and not just sit there, fine-tune some features to small clips and walk away and not understand what you're doing. Well, here at least you have the possibility. I mean, which kind of justifies why we've done what we've done. But okay, obviously you can criticize it, but I think annotation is somewhat useful, right? I mean, you have to have some annotations. Yeah, but it's useful. I mean, you cannot say it's not useful. The same thing for data collection. It's something which, I mean, which can be criticized, but if you don't collect any data, and basically what I said yesterday, basically all vision approaches and actions also need data, and so then you have to actually think how to get the data, right? And the second thing is for video, I mean, For images, you can still live with synthetic data, for example, but that's something for video. If you want to model how somebody evolves in a video synthetically, it's extremely hard again, right? So basically, this is also it's also much more difficult than in still images. I mean, if you look at the video games, I guess the environments, they're pretty well, like scenes, they're pretty well modeled. But if you look at the humans, I mean, at least the ones I looked at, they're pretty, like, very jerky, and the characters are skinny, and it's kind of a proxy, right? So it's not good enough to...
Like, I don't play video games, but like I think soccer or American football, I think it's motion capture. I think the motion must be very good.
Yeah, the motion is good, but the appearance is not so good. So basically, and so what we're currently doing is we have this surreal data set, which is our own synthetic data set, and we try to annotate the motion and combine these things. But in the end, if it looks too bad, then you cannot learn anything from it, right? And if it's too jittery and too noisy, and people have been creating these synthetic soccer games, for example, but if you look at it, it's very unrealistic. Obviously, the computer doesn't care if it's unrealistic or not, but basically, if you train on these things, I think it's still too far from the reality. So basically, what my personal impression is that for images, if the information is looks halfway good, you can learn from it, while for videos, for now, there's not much. Actually, there's not much for actions, right? It's not even videos, it's action. You can move the camera, or you can change the dynamics of the scene. And you can even move objects around. But for humans, I guess it's not even clear what precisely is the best representation, right? I mean, you don't know. I mean, okay, these 3D convolutional filters, they're a good proxy for what's going on in 2D. But if you think about what is the essence of human actions, it's not clear that it really captures what's going on, right? Because ideally, you would want to have some kind of representation to know which are the different parts and how these parts evolve over the video.
Yes, so that's
Yeah, actually, I have talked to people like this, and they don't give you the data, right? There's no way. Plus, you would want to animate the data yourself, right? What you would want is to get the full model and then be able to change around stuff and animate it, or or have like a lot of movies, right? And then basically, because you would probably need much more than one movie and the annotation. And we also try to get for the movie data, so you have these scripts, these transcripts, which go with the movies, right? That's something also what we've tried to get, and it's like things. It's clear there are things which you cannot get, and it's a pity, right? Because if you had them, maybe you could move faster. But at some point, I mean, the synthetic game engines, they will be better, and then basically maybe there will be a way to get away from these annotations and create things also which you can use for evaluation, right? Anyway, so basically what we have then is basically we can measure then how the human actions occur in the video, so you can really see how things evolve in these 15-minute video clips. So basically here in the beginning, it's very unlikely that people watch TV and fight, and it's very likely that people fight and do martial arts, so you can really see what actions appear together and which don't appear together, so you can really have some kind of statistics, and you can see also how actions transition in the video. So basically here you have, first you open the door, then you close it, you turn, then open, fall down, and then lie and sleep. So you can really see that by having this 15 minutes, you can measure how things evolve over the video. And then just to show actually what are the results on this new AVA data set. So these are the two traditional data sets, GHMBD and UCF 101 24 classes. The evaluation metric is average precision at 50% intersection over union threshold. And then the model which we have implemented here to evaluate the performance is similar to what we have seen in the beginning. We localize the humans, but then instead of just having a 2D convolutional network, we have a 3D, I3D network applied on RGB and flow. So we have these human detections, which characterize them as what type of action is going on inside the human box, and then we can combine these two types of information and classify a short clip of a human as performing an action or not. And then if you look at the performance on the different data sets, so this would be the state-of-the-art data sets, GHMBD, UCF 101. You can actually see that the performance is very good, almost saturated. What you can see here as well is by increasing the size of the 3D convolutional filters, so to 20 or 40, the performance improves. And then basically, if you look at the AVA data set, you can see that the performance is very low. So really, there's really room for improvement. So we're now, at the time we're at 16, now people are at 24%. So you can still really further improve the performance on this data set. And so basically, the question now is, what are the failure modes? So one failure mode would be that we are only modeling the actor and not the object or the environment the person interacting with. So for example here, there would be on the left a false answer for handshake. The person is really just reaching out the arm, but is not shaking a hand. This is because we don't model the other person's hand. Then here, a false answer for smoking. The person is really only covering the mouth. But given that we're not detecting the cigarette, we confuse the two. And then another false answer is here for writing. So the person is actually looking down and eating and not writing. But you could say, just given on the person pose, you could interpret that as writing. So this is the first failure mode. And then basically the second failure mode is also the problem. I don't have a slide here, but the problem is also that for many categories, you don't have enough training data. So you have this long tail distribution. And this is actually because we're having a model for the real world. We're annotating these 15-minute video clips. And many actions occur a lot of times. For example, standing or walking appears a lot of times. While things like swimming or falling down are very rare categories, right? And so basically that's giving you an imbalance in the training data. And what it also does during testing, it also gives you an imbalance in the testing results. But because in many cases for these very rare actions, you have a lot of negative answers which are incorrect. So basically it's a problem with the current measures that they don't take into account this imbalance of the data sets. Okay, and then so basically what I've been doing for this to model the interactions with the environment. So first, what we want is to not look at individual humans. I know I said before that these 3D convolutional filters look at the environment, but they don't really capture the evolution of the action over a longer time frame. What you really want to see if somebody is falling down is not just look at one frame and its environment. You want to see how somebody is evolving over the video. And I think this is something which is very important, which I'll come back to later, basically to see how to model longer temporal correlations in the video signal, right? You have a person which is evolving over time, and you don't want to have just something which is very short term. You want to really see how this person is evolving over time, and how do you capture actually this temporal context information. And so here what we do is we extract the humans, then we have, I'll get back to this in a moment, then I have a way of associating these humans over time to get the human actor tubelets, and then we do the same thing for the objects. We have a generic detector, a region proposal detector, which extracts potential regions for the objects. And then we have, on top of this, we have two types of models. One which models how these things evolve in time, the other one, how it interacts with the objects in space. And so how do we do the temporal dependence modeling? So basically, we have the human detector, and we construct tubelets based on the appearance similarity of the actors. So we have a Siamese network and triplet loss to see if actors are similar or dissimilar. And then once we have these tubelets, we extract individual features for each of the frames. And then we learn how to combine these tubelets, the features in the tubelets, with graph convolutions. So what people traditionally do, they just do average pooling. And so here, what we do on top of this, we learn how these features evolve over time. And so I'll show an example. For example, if somebody's walking, the motion is always the same, while if somebody's falling down, you have a different structure in your graph. And then the second part, we learn how the humans interact with the environment and other humans. And this is done weakly supervised, so we don't have the annotations. So what we have is these region proposals extracted, and we have some mechanism of backpropagating soft and assigning the features, which gives us a significance of the different object proposals. So if you see here, if you look at the performance improvement, you get a 6% performance improvement by adding these different types of relations. If you look here at the example, so here you have somebody is actually falling down. If you just use the baseline approach, you think that the person is sitting, so you just look at the middle frame. And then if you model how the appearance changes over the temporal sequence. You can then see that you actually correctly detect that the person is falling down because you give some importance to the last frame. And then the second thing is the illustration of how you model the relations. You can see here, if you just lose the baseline, if you just model what the person is doing, you say holding, it's not incorrect, you just look at what the pose of the person is. But then, given that you really want to predict that he's eating, if in addition you give a higher weight to the fork, you can really predict that the person is eating. So you're really learning how to model with the interactions to the environment. And so basically what we've seen, we improve the performance, but we're still not at whatever 70 or 80%. And so what is missing is what I said before, the training data and probably also the way you model interactions could be better. And also, yeah. I mean, it's clear that by adding the audio, you could have some improvements in the performance. But so two things: A, here we're just, I mean, you were interested in just improving the visual modality. Yeah. And B, we looked actually at the audio also at some point, and for many of the actions, it doesn't bring a big improvement in performance. So basically, if you look at, obviously you can always find very easy examples. For example, the dog barks or somebody shoots. I mean, then you can really see that there's a strong signal. Yeah. But other than that, we found that we actually looked at it. Other than that, we found for most of these categories, like for example, somebody is walking or falling down. Even falling down, maybe at the end there's like a big plunge. But other than that, from sitting down, there's not much, right? Obviously, talking, you would need audio, right? So I'm not saying you should not use audio, and that's actually something we're actually also looking at in particular if somebody is speaking, right? So then you get a much higher improvement in performance, because then you're not only using the audio, but you're also using the speech signals. I agree that in the long term, that's something you definitely want to look into, yeah. But we didn't do it here, and I think for the classes here, it didn't bring. I mean, so I mean the experiments we did here, they were just preliminary, so we did not use any noise cancelling, but. Yeah, but I mean, basically, just by looking what kind of audio you get, even for you, if I just give you the audio, you will not recognize what action is performed, right? So it was pretty clear just by just looking at the different categories that here there was not enough information there, and that's something. I mean, I think the noise cancelling, maybe you get 1 or 2% improvement, but like video stabilization, I mean, with convolutional filters, okay, I don't want to go into details here, but I mean, we tried it several times, and it brings you like 1% improvement, right? So you have this pre-processing for video stabilization, and then you get very minor improvement, even if it works, right? And so basically, this is because it's not something which the network is not robust against. So basically, we're just adding a bit of this noise during training. I would say you become robust to it. So. And then one thing which is also interesting, which we've been looking at, is future action prediction. So basically now we have looked at just action classification, localization, but in the long term, what you would want to do is to go one step further, to use your model and not be only able to say what is happening here and now, but also to predict what people are doing next. So here basically on the left, if you have a car, the camera in the car, you want to see if the person is likely to cross the street, yes or no. And then in the other example, you want to know if your daughter is going to fall down the stairs, yes or no. And so here, what we see here, basically they're sitting and talking, and what you would want to predict, so what's happening next is that they're clinking glasses, and then here they're standing and holding something, and next action would be serving, and then here hugging, standing, and next action would be kissing. And so here, what we have developed, again, is similar to what I've shown before, maybe a bit more complex, is an approach which models over space and time how the actions are evolving and how people and objects are interacting with the environment. And so here just what you have is you have the previous frames, you have the past, here the person is riding a horse, then she's stopping, talking, and then basically you could predict from this that the person will be getting off the horse, right? And so basically what you want to model is how things have evolved before and then what are the next actions. So here again what we showed is, A, basically by modeling this based on some person-specific activity, we can go beyond just pixel-based prediction. So many people, they just predict what's going to happen next based on the pixel information. Here we take into account the full model of the human and its interaction with the environment. And so here again, what we have is we have these region proposals. So we have a graphical model which models how the person is interacting with the objects in the environment. And then on top of this, we have a recurrent network which actually models how these things evolve over time. So before, basically they have a model of how it evolves before the action is happening, and then allows to predict what is the next action. So here we show that our approach outperforms some of the baselines. And then here you can see what we see here would be the frame on the left would be the frame which we are observing, and then on the right, the action which we're actually predicting. So basically, we're predicting eating, and then if you look at what's actually happening, is that you're eating. So one thing which is important here, obviously, is that you have probabilities of what's happening, right? So we cannot predict 100% certain what is happening, but you have some probabilities that the person is eating. Obviously, you could stop eating in the middle. Then here another example. On the left, what you see as input, so the frames before this, and then you predict that the person is getting up. Here, two more examples. And then here, two failure modes. So basically here on the top, you predict get up. So basically by seeing that the person is sitting, you think the person will get up immediately, but he's not getting up immediately, he's getting up later or never, I don't know. And then the second example is that you can have these multiple futures. So here we just display the best one. So basically here, you think that the person is closing the door, but instead of this, they are opening the door. Okay, and then basically, so one thing which is very important, which John also mentioned before, you don't want to annotate all the information in each and every frame. And so I present now two ways of actually doing weakly supervised learning of these actions. And the first one, what you have is you have different levels, varying levels of supervision. So basically on the top, you have only a label for the full video clip, and you want to localize in space and time where the actual action is performed, and then use that as a training signal, right? So if you just have this high-level label, you want to know where the action is actually happening, and use that as input to train your model. And then you can have different levels. You could also have in one frame annotated that in this frame the action is happening, or you could have the full temporal interval given, or you could have the full temporal interval given and a bounding box, one bounding box annotation. So here what we can have all these different levels of annotation. So this allows you actually to combine, for example, you could annotate the action in a few frames very precisely and then add more information, more videos for which you have very coarse annotations, and use that to mine automatically the information, right? So what you do here is you have these labels, and then from these labels, you localize where the actions are in space and time. So you get really this training data for free. And so the approach, which is here, so first we obtain the person tracks by automatic detection and linking. So we have as initialization the person tracks, and then the tracks are subdivided in short elements, which you call tracklets, where each tracklet is described the 3D convolutional network as a feature. And then what we want to do, if you have the tracklets and the possible action classes, we have this matrix of assignments that we assign a given tracklet to a given action class. So what we do now is you want to really label each of these tracklets as belonging to one of our, let's say, 20 different action categories. And so why do we subdivide into the tracklets? Because if you look at a human track, obviously it can be very long. So if you have like 1 hour of video, then the action will be only present in a very short clip. And then so here, obviously you can use different techniques for solving this problem. What we do here, it's based on discriminative clustering. So here the idea is you have a classifier, you have a predefined assignment, you have a classifier, and then basically what you iterate between assigning the labels to the given action classes and optimizing the classifier. So you training these two objectives jointly. You optimize this with the Frank-Wolf algorithm, and in the end you get a solution which kind of assigns a label to each of these tracklets. And what we do to initialize the person tracks is we have faster RCNN which extracts the person tracks. For the feature tracklets, we use the I3D features. And then if you look at the results, what we can see here, on the right, we have the full supervision. And then we decrease the level of annotation. What we can see, A, our approach outperforms the state of the art. And B, what we can see that by reducing the amount of annotation, our results up to some point, they're still very stable. And if you look at the second part, that's the DALY data set, if you have the annotation on the video level, so videos are a couple of minutes long, the performance degrades significantly. So basically, by having some good individualization, temporal individualization, you get better results, right? So for the UCF 101 data set where you have short clips, the performance is still very good. And then if you go to longer clips, it gets worse, right? Basically, and then the other problem which we have is how precise our human boxes are. So you can see here for the data set, for the UCF 101 data set, the boxes, they get worse if you don't have any bounding box annotation. And so you can actually see here that if you have the bounding box annotations which are trained on the UCF 101 data set, you get a 20% performance improvement. That's because you have all these very strange motions in there, and if you don't pre-train on these very strange motions, your performance degrades. So actually the take-home message here is basically if the videos are too long, it's really hard to mine information. So you have some kind of temporal interval where you know where to look in, like, or some temporal annotation here, this temporal point, that really helps you. So basically you could have just one annotation in the whole video telling you approximately where the action is. This helps you a lot. And then the other thing which is very important is to have precise human tracks. So basically if the tracks are not good, it's pretty clear then your regionalization doesn't work at all. And then if you look at the results, so here you can see, so here you have shot level annotation, here temporal point and bounding box. Here you can look at the results. So in green you have the ground truth. And you can see that by having one temporal point, as I said before, the performance improves significantly over only having the shot level annotation. And then here similarly, here it's like cleaning windows. So again, you can see this is the ground truth. By having shot level annotation, the localization is not perfect. By having the temporal point, you significantly improve the performance. And so what's nice here, here's another example. What's nice here is that you can actually combine different levels of supervision. So you can have, for a few examples, you can have the full annotation and then add the additional data in a weakly supervised way, show that improves the performance. So you can really combine these different levels of annotation. And then the second part for weak supervision, so this was the first part of weak supervision, more traditional. You have the human tracks. You want to mine which are the relevant informations, and then the second part is how to do learning with multimodal supervision. So here what we use is video and then audio to speech. So basically we have the audio signal and we transcribe it into words. And then the model we learn here relies on the BERT model to learn the correspondence between video and speech, and at the same time learns a temporal model for the video. And so here we use this for domains with sufficient training data. So for here we found that for cooking instructional videos, what you have is actually people, while they cook, they actually say what they're doing. So if you look at these instructional videos, people actually describe and say what they're doing. So here if you look at on the right, you can see if you transcribe what people are doing into text, you can really see that you have a very good recipe description of what's happening in the video, right? So basically, by just using this data, you can really see what's going on, and that kind of goes back to your question about the audio. So here, obviously, the audio is super useful because you really get a description and a signal from which you can actually not only use it as an additional information, but you can also use it to learn, right? Just by using this information, probably you could already see what's going on, but here the idea is to go one step further and use it actually as an additional weak training signal, right? Weak because it's not perfect. And so then we have collected this 300,000 cooking recipe videos on YouTube. This gives us an enormous corpus for training. And then what our approach is based on, it's based on the recent BERT model. So it's a bidirectional transformers for language understanding. So this model has shown that what it does is for sentences, it captures very precisely the context inside the sentence. So it's, if you're familiar with word-to-vec captures somehow the structure and the meaning of the word, but here you go one step further and you really model how the words in a sentence are characterized by their context. And so what it does is it takes as input two sentences, two adjacent sentences, and learns, this transformer learns the structure of the sentence. And how you train it is you mask out certain words and then predict them. So that's basically your training signal, is to mask out these words and then see if you can predict them just from their context information. So the idea is by masking out the words, you learn how to predict the context information. The second way they're training it, they're giving one sentence, you want to predict the second sentence. That again gives a very strong signal for training this transformer. What they have shown in language, in NLP, that this type of information can be used as pre-training. And so here what we did is we extended this to video. So what we do here, we have this transformer, this giant transformer, which takes as input language, but also the video. The video, we have to have some way of capturing or representing the video. So for language, what you have is you have the words. So they have in BERT they have a dictionary of 30,000 words. And then basically the question is, how do we replicate that in language? So we also have to have a set of words. So here our first approach was actually to cluster some video tokens. And the video presentation what we use here, again, is the C3D features, which we extract for 1.5 seconds of video information. So we take the video, we chunk it in short, very short clips of 1.5 seconds. Each of these for this 1.5 seconds, we extract here this C3D features or S3D features. So what we get, we take the pre-ultimate layer of 1,000 dimensions, which gives you a descriptor, gives us a descriptor of the video. And then the next step, in order to get these visual words, we cluster these descriptors with hierarchical k-means, and this gives us a set of clusters. And then we can actually use exactly the same formalism as we had for language to extract the visual features, right? So basically here we have the same thing, but instead of having language, we have these clusters, and we mask out some of the clusters and predict them correctly, or predict them as training signal. So once we have that, actually what can we do is we can just use this, just take the visual part to predict possible futures. We just take the one token and predict the other tokens as following tokens. You can see that the results are nice. We can see here basically you have this powder mixing, and you can see next steps of baking the cake. You can also use it. We can also see, okay, Jean doesn't like it, but it doesn't matter. You can also see that it's useful for illustrating sentences. So you have the sentence as input, and then predict the next token in the sequence to illustrate your recipe. I mean, okay, you can see that it does work, right? It's not always working, but it does work. Anyway, you have some more quantitative results for Jean. So basically, you can also measure. Obviously, you want to measure something. So basically, you want to see, does it actually learn this correlation between video and text? And so what we do is we have this template for the BERT model. Now show me how you mask the mask. So we want to predict what is the noun and what is the verb. And so we can then look what are the predictions. So here, the top verbs would be make, assemble, prepare. The top nouns, pizza, sauce, pasta. And then the second example, make, do, pour, and then the nouns cocktail, drink, glass. And then you have the UCook2 data set, where you have the annotations for the verbs and the objects. For each of the clips, you have annotated what are the verbs and the objects, and you can actually see that if you learn the model supervisedly or with our video BERT model, you can actually see that the performance is comparable. So you can really see that from this weak supervision, you can actually learn what are the verbs and the nouns in the corpus. And so basically, this video BERT model learns the video language correspondence. It approaches the fully supervised accuracy. And what's also nice to see is that actually the performance strongly depends on the size of the data which you have. So basically, the more data you have, the better you learn actually this video language correspondence. Okay, I have to hurry up. And then basically we also show that you can use this for caption prediction. Again, you outperform the S2D features trained by themselves. But now, then if you can use it also for action classification, you can actually see it fails. You can see that the performance actually drops significantly over just supervised learning. And so why is this the case? Basically, the case is that we have these clusters which are relatively uninformative, and so if you want to use them for a classification task, it's nice for prediction. Like correlation between text and language, text and videos is possible, but if you want to use it for prediction, it doesn't work. And so now, what do we have to do? We have to get rid of this step of clustering these features. We have to actually use this model to not predict the clusters, but to predict the features directly. And then once you have this architecture set up, you can also use it actually to learn not only the features which are pre-extracted, but also learn what is a good feature presentation. And so basically now we have to change a bit the learning objective. And here what we do is we use noise contrastive estimation to maximize the mutual information. And so what you have to do is we mine additional negatives to measure how these positives are different from the negatives and use this as training signal. And then on top of this, we have an additional layer. So now we don't learn the two models, the language and the vision model jointly, but we have an additional cross-modal transformer which combines them, so we can use actually the pre-trained language model and just train the visual model. And so if you look here, what we have our approach, so basically the language model now is fixed, and we just train the visual model. We can train it on different data sets. So here it's trained on how to 1 million and then kinetics. And then basically once we have that, we can either train just the transformer, or we can also train the S3D model. So we can also train the feature descriptor by itself. And then we have different tasks, classification, captioning, and just classification on standard data sets. And so basically our training objective is the noise contrastive estimation. And then negative examples are sampled from a distribution instead of a fixed vocabulary. And then compared to other contrastive predictive coding approaches, our approach is based on these bidirectional transformers and doesn't use RNNs. It replaces RNNs with these transformers. We have a second layer of this cross-modal objective on top of it, where we align the sequences of the speech and the video. And then if you look at the results, what you can see here is actually that here that's the window length. So basically this would be 1.5 seconds, and it's 72 seconds. You can see here the results for action anticipation. If you just do average pooling, you can see the performance remains roughly constant. Here, if you have an LSTM, performance goes up. And then if you use our transformers, the performance goes further up. But you can really see that this kind of allows you to measure the correlation and to learn the temporal correlation completely weakly supervised and apply it to a completely different data set, right? So it was trained on this. I think here it's trained on the how to 1 million data set. And you can show that for any of the standard data sets for action anticipation, it improves over the state of the art and really results in a better performance. And by looking how it captures the temporal context, you can really see that it's able to capture, 72 seconds is more than 1 minute of temporal context is captured correctly. The same thing for other data sets, salads and ActivityNet data set. And then here, what's nice is, as well, is that basically you can either train on the video only, or you can train on this cross-modal objective. You can see here, by adding the cross-modal objective, you get an performance improvement. So it's nice that you can learn from the video data by itself, but if you have this additional weak supervision, you can actually learn better temporal models. So here it's not about learning to predict one from the other, but it's learning how to model the temporal context. And then again, you can see that by adding more training data, you get an improvement in performance. And then so here, what is interesting as well, so for those who are familiar with the BERT model for language, I think they use 24 layers, and 16 attention heads. So that's internal parameters of the layers, are the layers of the transformer. The attention maps heads are how many of these different attention heads you have inside the transformer. And you can see here that in our case, actually 2 layers and 4 attention heads are sufficient. So basically, our model is much smaller than what they use for language. And so the question now is it because we have less data? So basically, in language, they use much larger data sets or corpuses for training, or is it due to that we have these continuous pre-trained features, which actually limits also the power of what can be learned? It's not clear where this difference comes from. And here, if you look here, we vary the layers, and here we vary the attention head. So it's like really much smaller models. And then the next step, so now, for now, we have only learned the temporal correlation, and then the question was, can you go further and also learn the features? So in the end of the day, what you would really want to do is to learn the temporal representation and the feature representation. And so here we train, I don't know how much time I have. We train on kinetics to be comparable to the state of the art. So one thing I said before, it's important actually to initialize with some kind of initialization of the network. Here we use rotation self-supervision, so just predict the rotation angle and use this as self-supervision. And then we use for evaluation, we use the 3D average pooled features plus a linear classifier. So here what you can see is that our approach actually outperforms significantly the state of the art of the self-supervised training of features. And here you can see that basically it compares different approaches, and here you can see that actually this 3D, predicting the 3D rotations already works pretty well, and then adding the transformer on top further improves the performance. And then here, this is fine-tuned and this is frozen. So basically frozen, you just learn the features, don't fine-tune them, and just learn the classifier. And what you can see here is that the results obtained with the self-supervision are still significantly lower than the performance of the state-of-the-art. So basically, you still have to improve the features, but you can see here that compared to what's around, we actually improve the performance over the most recent approaches. Okay, so I have to finish. So basically, we have seen that this masked language modeling works well for video, so we can really use this cross-modal self-supervision to improve the performance. What's nice is that we have seen that we can actually learn with these transformers how to capture longer temporal relations. And then next steps would be to see if we can go beyond cooking instruction videos to see if there's any audio information present which can be useful in other data sets. And then next steps are how can we further improve the self-supervised training. Okay, thank you.